Hello guys, today I'm going to show you how to apply the result of this analytical constraint optimal control for regulatory and servo systems to your own system. I'm just showing you here the result without any high-level mathematical manipulation and formulations. If you are interested in the derivations of the results of this paper, you can refer to these two papers. Please watch the YouTube video descriptions for the links. Optimal control is good, but constraint optimal control is superior. The most important things are not necessarily the most complicated. Problem formulation. This figure shows a first-order unstable system controlled by a PI controller. The problem here is to find the PI parameters Kc and tau I, such as to minimize this performance index, this objective function that consists of the error of the output of the system and the rate of change of the manipulated variable, and most importantly, subjected to these three constraints: the constraint on the output variable y, the constraint on the rate of change of the manipulated variable u prime, and the manipulated variable itself. Optimal means what? Optimal means we want to find the best manipulated variable or control variable. Let's move on. Before moving on, let me give you a quick note on the structure of the PID used in this paper. The normal PID controller looks like this. That means the manipulated variable is defined as proportional to the error between the output variable and the set point, and is also proportional to the sum of the error and proportional to the derivative of that error. This is the normal PID controller. E is defined as the difference between the set point and the actual output. The Laplace transform of the manipulated variable is given like this. But here, in this paper, we will use another PID structure that will help us eliminate the kick on the manipulated variable. This structure is usually called type C PID or IPD. For a normal PID controller or ideal PID controller, U is defined this way. The control variable is defined this way. But for the type C PID controller, the output variable is removed from the proportional and from the derivative terms, like this. The Laplace transform of that manipulated variable is given like this. This is the diagram of a normal PI controller, but we will not be using this. Instead, we will use a type C controller, also called IP controller. That means we are going to cut this link and linked it here, this plus sign will become minus. So this is basically the structure of an IP controller. In order to motivate the use of this second structure, let us go into MATLAB, into Simulink, and build this same model and compare the output and the manipulated variable. These are two block diagrams for this same system, 1 over s minus 1. For the first diagram, we use a normal PI controller, but for the second, we use the modified structure, the IP controller. Let's run it and compare the results. It's also important to notice that we use the same PI parameter. The integral term here is 1. The proportional term is 3. The integral term here is also 1. And the proportional term here is also 3. So we use the same PI parameters applied to the same system, only the structure differs. Let us run the system and compare both the output and the manipulated variable. What we notice here is that we have a peak. We have a manipulated variable peak here with the normal PI structure. And that's what we want to avoid using the second system. You can see that that peak has disappeared. So now that you understand the motivation of the IP control structure, let us jump into the results of this research. The first case here is when we don't really care about the limitation on the output variable, the manipulated variable, and the rate of change of the manipulated variable. That's called optimal unconstrained case. For the unconstrained case, the variable can be as high as we want. So there's no constraint. In that case, this is the optimal solution of the control system. Zeta here and tau c are the intermediate control parameters. Alpha and beta are given by this. As we can see, alpha only depends on the process parameter, the plant parameters k and tau, the input disturbance, and the weight on the output. Beta depends on the input disturbance and the weight on the rate of change of the manipulated variable. After computing the intermediate control parameter, we can compute the actual PI parameter using the following formula. The actual control parameter are Kc and tau I. As we can see from here, the optimal control parameters are explicitly defined in terms of the plant parameters. One thing also important to notice in this case is that the ratio of beta and alpha only depends on the ratio of the plant parameters and also the ratio of the weights. It doesn't depend on the input disturbance D, delta D. That means the optimal solution does not depend on the input disturbance. That's very important. The second case is when we set a high level of restriction on the rate of change of the manipulated variable. That means we don't want the rate of change of the manipulated variable to exceed a certain value. We want a smooth control. That's why the restriction is set on the rate of change of the manipulated variable. In this case, the solution is obtained by solving this set of equations. Our objective function is given by this equation. Our constraint function h is given by this equation, where x is defined like this in terms of zeta, and alpha and beta are defined like this. You can pause the video and observe that all these equations only depend on two parameters, zeta and tau c, which are the intermediate control parameters. All other parameters are the plant parameters k and tau. We also have u prime max, which is none, delta d, which is assumed to be none or can be estimated. This set of equations are explicit equations that can be easily solved in any numerical tools like MATLAB, Maple, Mathematica, and the like. The case C is when a high level of constraint is applied to the output variable, to the process variable. In this case, we don't want the output variable to exceed a certain value. In this case, the constraint optimal solution can be obtained by solving this set of equations. Again, you can pause the video and observe that these are explicit equations that only depends on zeta and tau c, which are the intermediate control parameters that we are looking for. The case D is when a high level of constraint is put on the output variable y max and the rate of change of the manipulated variable. In this case, the constraint optimal solution can be obtained by solving this set of equations, which again are explicit equations. The case E is when a high level of constraint is put only on the manipulated variable. In this case, we want the control variable, the manipulated variable, not to exceed a certain value. In this case, the optimal constraint solution can be obtained by solving this set of equations. Again, you can pause the video and observe that all these equations are explicit equations that only depends on the control parameter zeta and tau c. Case F is when a high level of constraint is put on the process variable y and the manipulated variable u. In this case, the constraint optimal solution is obtained by solving this set of equations, which are explicit equations. And the last case here is when a very high restriction is applied on the manipulated variable and on the rate of change of the manipulated variable. In this case, the constraint optimal solution can be obtained by solving this explicit set of equations. After obtaining the optimum solution of the control parameters tau c and zeta, we can now use that to calculate the actual PI parameters, case C optimum and tau I optimum, using these two equations. Let's take a typical example. Let's assume K and tau is 10. The plant will be given like 10 over 10s minus 1. Using all the previous equations, we could make typical examples for all the cases. If you observe here, in case A, we set high values for Y max, U max, and U prime max, meaning that there's no constraint applied on those variables. And our algorithm automatically found the optimum parameters Kc and tau I for this case. Now for case B, what changed is we reduce U prime max. So we set the constraint on the rate of change of the manipulated variable by reducing it. And our algorithm in this case automatically gives us the optimum constraint parameters Kc and tau I for this case, without any trial and error. The difference from case A to case C is that we apply a high level of restriction only on the output variable Y. And in this case, again, we automatically obtained the control parameters. For case D, we set restriction on both the process variable Y and the rate of change of the manipulated variable U prime. We automatically obtained the optimum control parameters Kc and tau I. For case E, we only set restriction to the manipulated variable and automatically obtained the control parameters. For case F, we set a restriction on the process variable Y and the manipulated variable U. For case G, we set restriction on both the manipulated variable U and the rate of change of the manipulated variable. So as you can observe, with this algorithm, you automatically obtained the control parameters Kc and tau I that will lead to an optimum value, I mean the best value possible of the manipulated variable, while taking into account all the constraints set on those variables. This is the time response plot for case A to D. As you can observe, for case A, we set high value of constraints. In other words, there's no constraints on any variable. For case B, we only care about the rate of change of the manipulated variable. As you can see, we obtained the optimum solution that satisfies the constraint on the rate of change of the manipulated variable. For case C, the constraint is satisfied for the process variable. For case D, the constraints are satisfied for the process variable as well as for the rate of change of the manipulated variable. For case E, the constraint is satisfied for the manipulated variable. For case F, the constraints are both satisfied for the process variable and the manipulated variable. And for the last case, the constraints are satisfied both for the manipulated variable and for the rate of change of the manipulated variable. I can assure you that you can directly use the results included in this video to automatically generate and compute the PI control parameters that will lead to an optimal solution that satisfies the constraints. And the best part is that all those equations are explicit equations. All those solutions are explicit. That means the control parameters are obtained on a closed form. That's pretty it. Note that all the results that I just showed you are just for unstable system. For stable system, you can just change k and tau to minus. There is also another paper for stable system. If you are interested in that, please refer to the two papers I just showed you. Those papers are well detailed, and there are many other things included in those papers that I didn't include in this video, like how to choose a feasible constraint set, because your constraint set will not be satisfied every time. That paper shows you how to make your constraint set to be feasible, and many more. So we really advise you to read those papers and to pull out useful informations. The idea of this paper originated from Professor Moon-Young Lee, the chair professor of the Process System Design and Control Laboratory in Gyeongsan, Daegu, South Korea. Thank you, Professor Moon-Young Lee, for all your time, for all your availability, and especially for your patience. The project was initiated by him, and then Mrs. Hien also worked on the project, a female master student. She developed Nash mathematical equations to solve servo system analytically. And then Dr. Chamna took the project to the next level. There are some limitations to this research though. The results of this research can be applied only for single input, single output, first order system. That means there are plenty of rooms for extension of this research. I hope this video motivates you to initiate a research based on analytical constraint optimal control, and I also hope you apply it to a practical project. And if you do so, please kindly share the result with us. Thank you. See you in the next video. Bye for now.